Hi students. In this lecture, I am going to discuss previous IIT questions. Let us see first one. Let's see first one. A loop carrying current I lies in the xy plane as shown in the figure. The unit vector k cap is coming out of the plane of the paper. The magnetic moment of the current loop is, you can see diagram here. It is in xy plane and given this length is a and current is now I. So we have to calculate magnetic moment of the loop. Let us see how to start. Right. First of all, see the given diagram. So in this, we have to calculate magnetic moment, which is given by m bar equal to I n a bar. Okay. And directions, you can see diagram once. So diagram is like this. And this is x-axis. And this is y-axis. And coming to the length, so this is given as A. So it is just like a square of side length A. Now we have to focus direction of current, and that is given. We can see here direction of current. It is given anti-clockwise, right? Given anti-clockwise, current is I. So M bar. First focus here, what is area? So coming to area, for this part, it is a square. So area is now A square. Next, focus this a half circle. And for that area will be pi r square by 2. And you can see radius. This is now 2r. Radius will be, it is a by 2. So pi r square by 2. That is area of semicircle. Okay. Legs are having now 4. 1, 2, 3, 4. So into 4. This is now area of this loop. Okay. Number of turns. It is only 1. So into 1. Into I. Current is given I. Right. It is I. Now focus direction part. Current is now given anti-clockwise. So take your right hand and curl fingers anti-clockwise. Taking right hand, okay? Then thumb will be pointing towards us. I am repeating. So take right hand, curl fingers anti-clockwise because current is anti-clockwise. Then thumb is now pointing towards us. That means it is direction will be positive z axis. It is given here k cap is coming out of the plane of the paper. So direction part will be, it is a k cap. So into k cap. That is m bar. Now see which options are correct. So first I'm cross checking the direction part. Except C remaining all given k cap. Next focus here area how much. So definitely A is not correct. So we have to focus now B and D. See here what we get. A by 2 whole square. Here 4 is there. That gets cancelled. So remaining is now A square. I am taking A square outside. So it is 1 plus pi by 2. 1 plus pi by 2 into y. Means we can say option B. Pi by 2 plus 1 into A square into y. Direction is k cap. That is magnetic dipole moment. That means this current carrying loop is acting as a acting as a magnet, and you can see which phase is acting as north pole and south pole. You can see here, if you are taking south pole, direction of current must be clockwise. Okay, if it is a clockwise, then that phase will act as south, and if direction is anti-clockwise, okay, then that phase will act as north. You can see in this, direction of current is anti-clockwise. That means this phase is acting as north pole. The phase behind this is acting as south pole. And we have learned that direction of magnetic dipole moment is from south to north pole. That means it is outwards. That is what we have taken here, K cap. Okay. Now see next one. See next problem. A conducting loop carrying current I is placed in a uniform magnetic field pointing into the plane of the paper action. We can see here conducting loop. Current is given clockwise and field. It is pointing into the plane of the paper. The loop will have a tendency to contract, expand, and next to move towards positive x-axis, to move towards negative x-axis. So here first thing we have to focus, it is placed in a uniform magnetic field. So when a conducting loop is placed in a uniform magnetic field, net force equal to 0. That means option C and D are not correct, because net force 0 means it does not move. Okay. Now we have to focus option A and B. Let us say how to verify. It is given clockwise. Field is into the paper. So current is clockwise. Current is clockwise. And field is into the paper. Cross circle. Okay. Now see what we can do. Let us consider one small element here. Force acting on a current carrying conductor. So we have learned that F bar equal to I into L bar cross B bar. Okay. This is what we have learned. Means when you are taking a straight current carrying conductor, force acting on that. Okay. Let me take this is x-axis and this is y-axis. Okay. Now focus carefully. Force acting on this part of the wire, only on this part. In this part, we can see direction of current. It is right side. Okay. Direction of current is right side. Focus only that small part. Direction of current right side. So L bar direction is right side means I cap. Okay. So I'm focusing now direction of force. Direction of L bar is direction of current. It is on right side. That is I cap cross B bar. It is given into the plane of the paper. According to this, into the plane of the paper means it is minus K cap. Okay. So I cap cross minus K cap. Now see what we get. I cap, J cap, K cap. If you are taking K cap cross I cap, that is J cap. It is I cap cross minus K cap. I cap cross K cap minus J cap. Minus into minus plus. It is J cap. That means on this part of the wire, force is now outwards. Now focus diametrically opposite point. Take one small part here. Direction of current. It is left side, right? Direction of current is left side. Direction of B remains same. So only changes now direction of L bar. In the place of I cap, it is minus I cap. That means on this one, direction of force, it will become minus J cap. That means direction of force will be outwards again. So it is outwards. This is also outwards. We get same condition at each and every point outwards. Force is outwards. It has a tendency to expand. Okay. It has a tendency to expand because force is now outwards. Right. So option is it is B. Right. Let us see next one. A thin flexible wire of length L is connected to two adjacent fixed points and carries a current I in the clockwise direction as shown in the figure. When the system is put in a uniform magnetic field of strength B going into the plane of the paper, the wire takes the shape of a circle. The tension the wire is. Okay. You can see here diagram. Field into the paper, direction of current clockwise. You can see the previous question and this question both are same, right? See carefully. Direction of field into the paper, current clockwise. The only thing is that here we have to calculate tension, right? Let us see how to start. Into the paper clockwise. Given wire length is L, we have to find tension. Let us see how to start. So again, it is same question. Circular shape. So we got a conclusion that force acting, that is outwards. Okay. So I am taking here one small part on the wire. So take a small part and that small part subtends an angle d theta at center. That small part subtends a small angle that is now d theta at the center. Okay. Now you can see this remaining part of the wire, it is now pulling this small part. So this is very small part. Just to make it visible, I'm showing it is somewhat large. Okay. It is a small part. So on this part, by remaining part of the wire, tension along a tangent, it is like this tension T and tension T. Now you can see components for this one component left side and for this component right side. These two will get cancelled. Okay. Remaining will be towards center. This component and this component. These two are now towards the center. Okay. Sum of these two. That will be 2t sine d theta by 2. So we have taken this number of terms earlier, right? So components, these two are towards the center. Now, this force must be balanced by force due to magnetic field because this element is now in equilibrium. Now ring is in equilibrium. That means if you take any small part on the wire, that will be in equilibrium. That means net force equal to 0. Therefore, this tension force must be balanced by force due to magnetic field, right? This is equal to, say, magnetic force how much? F bar, that is equal to I into L bar cross B bar. Okay. So here you can see field is into the paper. L bar, direction of L bar is, it is direction of current. Okay. That is direction of current is in this element, it is right side. Okay. So it is now, I am writing here I into current is I. So between L bar and B bar angle is 90. Okay, between these two vectors angle is 90. So I into L, length. Length of this arc, that is R into d theta, right? This arc length, I into L into B. And remain just calculation part. Since d theta very small, sine d theta by 2 sine d theta by 2 approximately equal to d theta by 2. Substitute there 2t d theta by 2, that is equal to I into R into d theta into B. Right. Now simplify this. 2 gets cancelled, d theta gets cancelled. So tension equal to IRB. Okay. Now in the problem, it is given length equal to L, length. That length equal to 2 pi R. So in the place of R, we can write. So in the place of R, we can write it is L by 2 pi. So L by 2 pi into B. So ILB by 2. Okay. Let us see next problem. So here correct option is, it is C. C is correct one. See the next one. A uniform magnetic field B exists in the region between x equal to 0 and x equal to 3R by 2, pointing normally into the plane of the paper. A particle with charge Q and momentum P directed along its axis enters region 2 from region 1 at point P1, and for this point it is given y coordinate minus R. Which of the following options are correct? Given 2017 advance. See diagram. Region 1, region 2, region 3. In fact, almost same kind of question we have discussed earlier, okay, in the last lecture. And we can see options. Particle re-enter region 1, will enter region 3, right? Already we have discussed these kind of questions. If this value 3R by 2, if it is greater than or equal to R, then it will re-enter region 1. In that case, it follows semicircular path, right? Next, if it is less than R, less than radius, then it enters into region 3. Okay. And you can see option C and option D. Let us see. First of all, make the given diagram. See what is given here. Right. First of all, diagram it is. This is region 2, 1, and this is given this length is 3r by 2. And it is given this enters, and this particle enters at y equal to minus r. Enters here. This is y equal to minus. So this is now x-axis. Right. Now first focus condition to enter into region 1. If radius, or you can say this 3r by 2, if it is less than radius, wait, to enter into region 1, right? Region 1 means if this is greater than right. So if this is greater than or equal to radius, okay. If this is greater than or equal to radius, in that case, it follows semicircular path. It is like this. Equal to means it will touch this line. Okay, it will go like this. Okay, in this way. If it is equal, what happens is when it completes 1/4 revolution, it will touch this boundary. This is when 3r by 2 is equal to r. Then again, it comes back like this. Okay. So condition is that 3r by 2 should be greater than or equal to radius. Now radius how much? It is in this data given. Let me cross check once the data given here. Right. It is given field B, momentum P. That means I can write it in the place of MV, in the place of MVP, MV by B. Okay. So from this we can write V value should be greater than or equal to 2 by 3 into P by R cube. Okay. That is now condition. Now see options. Coming to first option, 2 by 3 into P by QR. It will re-enter region 1. So it is correct. So here equal to also possible. Equal to means what happens? Just touches this boundary and again comes like this. Okay. So equal to also correct only. So given greater than. So it's correct only. Next. Coming to option B. Given it is now 8 by 13. See which is more? 2 by 3. 2 by 3 means 0.67, right? And what about 8 by 13? See how many times? It is, if I'm taking 6 times, 6, 13, 78, right? That means this is definitely less than 2 by 3. That means it will definitely enter into region 3. Okay. So option B is correct because that is nothing but satisfying the condition 3r by 2 is less than r. Okay. 8 by 13 is less than 2 by 3. That means it will enter into region 3. Okay. So option B is correct. Now focus option C. See sentence carefully. When the particle re-enters region 1 through the longest possible path in region 2, the magnitude of the change in its linear momentum between the point P1 and farthest point from y-axis is P by root 2. So you have to focus sentence carefully. Re-enters region 1 through the longest possible path. Longest possible path means it has to follow semicircular path. Okay. Condition 1. The magnitude of the change in its linear momentum between the point P1 and the farthest point from y-axis is. So for example, this is now P1. Okay. Farthest point means one velocity vector is normal to its initial velocity vector. The direction is now like this. Okay. This is now direction is like this. So in this case, we can see now we are knowing that direction of momentum changing but not magnitude. If this magnitude is P, this also P only. Between these two vectors, angle is now 90. Therefore, resultant will be, it is root 2P. Okay. So this is a P magnitude, this also P. Between these two angles 90. Therefore, resultant is root 2P. Right? But given P by root 2. That's why it is not correct. Okay. Next. Coming to option D. For a fixed B, particles of same charge and same velocity, distance between point P1 and the point of re-entry into region 1 is inversely proportional to mass of the particle. You can see here, while coming outside, distance between these two points, this is equal to 2r. Okay. This distance equal to how much? It is 2r. And see what is r value? R equal to mv by bq. So distance equal to 2r. Now see option given for fixed b. So b value fixed. B value fixed. Same charge. Q value same. Same velocity. B value same. What is left here? It is only mass. That means it is a proportional to mass. But it is given inversely proportional to. Okay. That's why option D is not correct. So correct options are A is correct and B also correct. Okay. Let us see the next problem. Let's see the question given. A potential difference of 600 volt is applied across the plates of a parallel plate condenser. The separation between the plates is 3 mm. An electron projected vertically parallel to the plates with a velocity 2 10 power 6 meter per second moves undeflected between the plates. You can see diagram here. Find the magnitude and direction of the magnetic field in the region between the condenser plates. Neglect edge effects. Okay. Asked for 3 marks in 1981. Let us see how to start. Let's see first of all that given diagram. So diagram is so given two plates, this is a charge positive and this is negative, and this is grounded, projecting electron right in between the plates like this. Okay, let us consider this is X and this is Y. Okay, right. And see what else given here. Potential difference is 600. Potential difference is 600 volt. Separation between the plates. Separation between the plates given 3 mm. 3 mm. Velocity given. Velocity 2 10 power 6 meter per second. Now condition is magnitude and direction of magnetic field in the region between the condenser plates. And see, this is for what? This condition is it has to move undeflected. No deflection. No deflection means velocity is constant. Okay. Velocity direction is not changing. Direction of velocity not changing means so we have taken net force equal to 0. Okay. We can say force acting on electron because of electric field Q into E bar, because of magnetic field Q into V bar cross B bar. Now this value must be 0. If this is 0, it goes now without any deflection. Okay. And you can see strength of the electric field. Potential difference by separation between plates. 3 10 power minus 3. Right? Millimeter, right? So 10 power minus 3. This is 2 times. It is now 2 10 power 5 volt per meter. That is electric field. Now this is equal to 0 means from that I can write since charge is not 0, E bar plus V bar cross B bar should be 0 bar. Okay. So from this I can write E bar is equal to negative of V bar cross B bar. Okay. Now you can see in the diagram, direction of electric field. It is positive plate to negative plate. That means it is positive x-axis. Direction of electric field. It is a positive x-axis, means I cap. So I cap. Here we are having negative sign. Direction of velocity. It is given according to this velocity is now along positive axis. So I have to take here J cap cross B bar. Coming to B bar, that is direction part we have to decide now, right? Direction part. So J cap cross something and having a negative sign. So this something must be minus K cap, right? If this is minus K cap, then J cap cross K cap, that is I cap. Here I am having, so let me cross check, J cap cross minus K cap, that is minus I cap. Minus of minus becomes a plus. So direction of the field, according to this convention X and Y, field must be into the board. Okay, it must be inwards direction. And coming to modulus value, When it is inwards, between V bar and B bar, angle is 90. See carefully. Velocity along y-axis, field along negative z-axis. Between these two vectors, angle is 90. So if you focus now modulus value, E equal to V into B into sine 90. Okay. So from this we can get B value. B equal to how much? So B equal to E by V. So I hope you can make calculation by substituting the values, because E value, it is 2 10 power 5. V value, V is here, what is that velocity, right? This is velocity. So this is 2 10 power 5. Velocity given 2 10 power 6. So 2 gets cancelled. It is now 10 power minus 1, means 0.1 Tesla. Okay. So key point is that net force 0. So electric force plus magnetic force, net is 0. From that, first we got direction, or you can say direction of field. That is now angle between V bar, B bar is 90. So coming to magnitude, E equal to V into B into sine 90. Okay. So I hope you got the clarity.